In this lecture, we are going to study what is light. Light is a wave or light is a particle. To understand that, we are going to discuss some phenomena of light like diffraction, interference, and polarization, and also we will see what is the photoelectric effect. Many scientists through the ages tried to answer the question, what is light? In 1600, the nature of the light became a topic of debate. Isaac Newton favored the particle model because the light traveled a straight line and the light also followed the law of motion. The light has energy, a velocity like any particle. Almost at the same time, Christian Huygens, he believed the best model that explained the nature of the light was a wave model, because light has a frequency, a wavelength like a wave. Then he believed the light is not a string of particles, rather a longitudinal wave. And this happened at this time, yes, between 1600s and 1800s. Then let's see what happened during 1800s. Then, as we say, during 1700s, Newton's particles theory was favored by many. But during 1800, more and more experimental evidence showed that the light can be explained if the light was a wave. Let's see what was the experimental evidence that was found in 1800 that showed the light was a wave. And first one is the diffraction. Remember, diffraction occurs when the wave can travel around the edges of obstacles or pass through small openings. And in case of the light, diffraction occurs when the light wave passes by a corner or through a small opening or a slit, like in the figure we had in this case. And the light can pass through the opening even if the opening is the approximate size or a small size than the light's wavelength. And what happened is we cannot explain this result if the light is a particle. For example, if we had a ball, yes, this ball is like a particle. If we had this, it's like ball, yes, and we had this opening, then the ball is like, the behavior of the ball is like a particle. And if we had this opening, then we cannot pass the ball through this opening. Yes. Then what happened with the light if the wavelength of the light is even larger than the opening? Then what happened is the light can pass through this opening. Then we cannot explain that if the light is a particle. The only way can be explained this result if the light is a wave. In the 1800s, Thomas Young conducted the experiment is called the double slit experiment that proved the wave theory of light. In his experiment, he produced a pattern of bright lines and dark zones. This happened because the light produced the phenomenon is called the interference. Then the bright lines or bright zones correspond to the constructed interference, and the dark zone or dark lines correspond to the destructed interference. This phenomenon can be explained only if the light is a wave. And at this point, the scientists were agreeing that light must be a wave. Now we had another phenomenon associated with light, which is polarization. In the first picture, we had unpolarized light. This consists of vibration of the light in all directions. In the second picture, we had polarized light, means the light can be vibrate only in one direction, in this case, in vertical direction. And what happened is we had a crystals that allowed the light pass only in one direction, for example, in vertical direction. And if we had two crystals at the end, we will have light like similar at the other light. We cannot distinguish if the light is polarized or unpolarized. But what happened if we had this experiment? If we had crystals that allowed pass the light only in vertical direction, and then we had another crystal that allowed to pass the light in horizontal direction. If we cross these two crystals, then what is the result? No light at the end. And this is, in this way, we know it's possible to polarize the light. And what happened in the 1800s is this phenomenon cannot explain neither by particles model of the light, nor by wave model if the light was considered as longitudinal wave. The only way this phenomenon can be explained is if the light is considered a transverse wave. And this experiment helped to understand that the light is a transverse wave, it's not a longitudinal wave. In this example, we had two polarizers. This polarized the light in horizontal direction. This polarized the light in vertical direction. And we can see when we cross these two polarizers, then it's not possible to see it through them, as there is no light. One of the applications of this phenomenon is the sunglasses, polarized sunglasses. And usually the polarized sunglasses, they block this direction of the light, and the lenses allow pass this direction of the light. And this is why we can see a better image as when we use a polarized lens, because there is less scatter of light. An additional point that favored the light wave theory was that Maxwell proposed that light was an electromagnetic wave. Remember, the electromagnetic wave is a combination of electric and magnetic fields that are perpendicular each other. During 1800s, all the experimental results along with the electromagnetic wave theory showed that the light was a wave. However, there was some phenomena that wave theory cannot explain. That phenomenon is related to the absorption or emission of the light from matter. And let's see what is that phenomenon. The results of the photoelectric effect experiment can be now explained if the light is considered as a wave. And let's see in what consists this experiment. Before talking about the setup of the experiment, let's see what happened with the light interact with the matter. Light, which is an energy, when interact with the matter, that matter absorbs that energy. If that material acquires energy and pass this energy to the electrons, sometimes they give enough energy to the electrons and the electrons can escape from the material. And let's see now what was the setup that was used by Max Planck when he conducted the photoelectric effect experiment. And in this setup, he has two plates. One is negative charged plate, the other is positively charged plate, and also he has a source of power and a device that he used to measure the current of the circuit. Then what happened is, when the light strikes the negatively charged plate, they give enough energy to the material, and some electrons can escape from the material. That electrons are attracted by the positively charged plate, and these electrons can move through the wire as a flow of electrons, creating a current in the circuit. And this current was measured using this device. Then in this experiment, the number and energy of the electrons were measured when the light intensity was low, when the light intensity was high, and also different frequencies was used when they conducted the experiment. Let's see what were the results obtained by Max Planck when he conducted the photoelectric effect experiment. And he observed, when he radiated the plate with the red light, he didn't see any emission. It indicates that the red light didn't give enough energy to the material, so the electrons cannot escape from that material. But if he radiated the plate using the green light or the blue light, then he observed some of the electrons can escape from the material. Means the green light or the blue light give enough energy to the electrons so they can escape from the material. And also, after he collected the measurements, he found these results. First, low intensity light ejects fewer electrons. High intensity light ejects many electrons. However, all the electrons have the same kinetic energy. Means the kinetic energy is independent of the intensity. Then let's try to understand these first 4 points. Then we know the intensity is the power per unit area. And the power is the rate of energy. It is how much energy per unit time. If we combine these two equations, then we will have the intensity equals to the rate of energy per unit area. We can see in this equation, that is the equation that explains the intensity in any wave. Yes, the intensity depends on the energy. Yes, more energy, more intensity, less energy, less intensity. But it doesn't happen in this case, yes, because it's low intensity, high intensity, same kinetic energy. Then the wave theory cannot explain this behavior. Yes, because why, if they had different intensity of energy, they had different energy, then the wave theory of light cannot explain why, if you radiate the material with low intensity light and high intensity light, you get the same kinetic energy. If in case of the wave, for example sound, the energy depends on the intensity. Then one more thing he observed was the kinetic energy is related to the frequency, means depend on the color of the light. Then if he radiate with, for example, with blue light, then he got what value for kinetic energy. If he radiate the plate with blue light, then he got some value for the kinetic energy. Means that kinetic energy depends on the frequency of the light. wave theory can not explain this behavior of the light. One of the scientists that helped to understand these results was Albert Einstein. He proposed that the light was a photon. And let's see how he explained the results obtained by Max Planck. Albert Einstein, he explained the results obtained by Max Planck based on the idea of quantization of energy. In 1900, Max Planck, he explained his results. He considered the vibrating molecules can emit light only in discrete amount of energy, means some particular values. And this discrete amount of energy he called quanta. In 1905, Albert Einstein, he applied the quantization of energy concept to the problem of photoelectric effect. He described the energy in light waves as a quanta of energy. It's like a package of energy in the light wave. And to this package of energy that Max Planck called quanta, he called photons. And each photon has an energy equals to h times f, when h corresponds to the Planck constant is just a number, and f corresponds to the frequency of the light. And this is why in his results, Max Planck, he found the energy, the kinetic energy of the electrons depend on the color. In other words, the kinetic energy of the electrons depend on the frequency of the light. Let's see how Albert Einstein, he found the relation that the kinetic energy equals to h times f, is h times frequency. Then he plotted the kinetic energy versus frequency using the results obtained by Max Planck, and he found the relation between kinetic energy and frequency was a linear relation. And using different data, he found also the constant of proportionality, means the slope was always equals to this value. And he called to this value the Planck constant. Because it's a linear relation, then we can model these results. We can fit this data using the linear relation. In y-axis, we had the kinetic energy. In the x, we had the frequency. Yes, this is the x. We had the frequency. Y, we had the kinetic energy. This is why here we had f. The constant of proportionality means the slope is the h value. Yes, is the Planck constant is this value, which is here. And this phi function is the y-intercept. Is the minimum energy that is needed to take off the electrons. This is the minimum energy that electrons need to escape from the material. And this is how he, using just a linear relation, he was able to obtain the equation that describes the results obtained by Max Planck. Because of this explanation, which is just a simple linear relation, he won the Nobel Prize on 1921 because of the explanation of the photoelectric effect. Let's apply the equation obtained by Albert Einstein to solve this problem. Then in this case, we want to calculate what is the energy of a photon. It's just for one photon of red light with a frequency of 4 × 10⁻14 Hz. Then we know the frequency of the light, and you can see because it's red light is a visible light. Yes, this is why the power of 10 is 10 to the power 14, because it's a visible light. We know the Planck constant, which is 6.63 10 to the power minus 34 joules per second. And we want to find the energy just for one photon. Yes, this is we are going to calculate now. And if we apply this equation, and the energy equals to H joules per second times the frequency, but the frequency is 4.00 10 to the power 14, and we know hertz means 1/second. Right here is 1/second, because it's an energy, is an energy. We expected joules. Then we can see this to cancel out, and we had joules in the answer. Yes, this is the unit we expected. Now, if we multiply the numbers together, 6.63 times 4, we will get 26.5. And negative 34 plus 14 will be negative 20 joules. If we want to write this in scientific notation, we move one place. Then we move one place to the left, means we need to add 1. Yes, we need to add 1. And the energy will be 2.65 10 to the power. Negative 20 plus 1 will be negative 19 joules. Also, you can multiply using your calculator, and you will get directly in scientific notation. Yes. And it's important, you see this energy is really a small value, it's 2.65 10 to the power minus 19. But you have to take into account this is the energy just for one photon, yes? Just for one package of energy. If we had millions of photons, then we will have enough amount of energy. Yes, then this is why this value is really small. And this is the answer. Then finally, what is the present theory about the nature of the light? Then we had two models, the particle model and the wave model. Then the particle model, they explain how the light travels in the space. Also, if we consider the particle model, we can explain phenomena such as photoelectric effect. If we consider the light as a wave, then using this model is possible to explain how the light is emitted or absorbed by matter. Also, it's possible to explain phenomena such as refraction, interference, diffraction, polarization, and interference. And in conclusion, today the light is considered to have a dual nature, sometimes acting as a wave and sometimes acting as a particle. But light never exhibits both properties at the same time. And this is the present theory about the nature of the light. And this is all I had to discuss for today.